Hi, my name's Tony Preston, and in this short video we're going to run through some of the basic functionality of Agilent's N9343C 13.6 GHz Handheld Spectrum Analyzer. If you want to learn more about the N9343C, make sure you get a copy of the complete user training and application tutorial DVD, which you can obtain free of charge from Agilent. It runs for about an hour and provides far more detailed training on a whole range of practical topics, such as making interference measurements, measuring modulation characteristics of carriers, sweeping diplexers, and other practical measurement examples. And if you've not done so already, you might want to download the PDF of this Agilent N9343C demonstration guide so you can follow along during the course of this presentation. Let's start with a quick overview of the instrument. As you can see, the instrument is extremely rugged and ideal for field operations. In addition, it has an extremely bright daylight viewable display, ideal for use outdoors in bright conditions. But when working in a communications room or other dark environment, the built-in light sensor can be set to automatically reduce the screen's brightness, making the display easier to view and saving battery life. When we dim the studio lights, you can see that all the front panel keys have a backlight that can be set to automatically turn on when required. Just refer to page 6 of the demonstration guide for details on how to configure this. On the top panel, we have the main RF input, the DC jack for externally powering the instrument or charging the internal battery, a small USB connector for connecting the instrument to a PC, a large USB socket for a USB memory stick, audio headphone out for listening to demodulated audio, an Ethernet connector to connect the instrument to a local area network, an RF output socket if you have the internal tracking generator option installed, a probe power socket for connecting an active RF probe, a dual-purpose BNC socket for connecting an external 10 MHz reference clock or externally triggering the spectrum analyzer. And even though the instrument has a built-in GPS receiver and internal antenna, you can also connect an external GPS antenna to this socket here. Here's the instrument's power button. Just press that to toggle the instrument on and off. And to the right are a range of function keys for setting parameters such as the frequency, span, amplitude, bandwidth, etc. And press the shift button for functions such as save and recall, adjusting display settings, the sweep time, etc. As with most Agilent instruments, there are 3 ways of adjusting a value, using the numeric keypad, the up-down arrow keys, or by turning the knob. If we want to put a marker on the signal, just press the marker button. And you'll see to the right of the display, there are 7 soft keys, the meaning of which changes depending on which function key we have pressed. And of course the most important button on the instrument preset button. Pressing the green preset button presets the instrument to a factory default state, clearing any strange settings that a previous operator may have used. Let's start by making some simple measurements of a 2 GHz RF carrier that's being generated by this Agilent MXG signal generator I have here. So we press frequency, select center frequency and enter 2 GHz. That moves the signal to the center of the screen. Then we adjust the span to 10 MHz and you can see the signal more clearly across the display. Then press the amplitude button and we'll set the reference level to -10 dBm. And if we want to measure the amplitude and frequency of that signal, just press the marker button and you can see here marker 1 is at 2 GHz and the amplitude is about -10 dBm. And if I turn on some modulation on the signal generator, you can now see we have a WCDMA modulated signal centered on 2 GHz. Here I'm going to be saving files to the analyzer's internal memory, but be aware you can just as easily save and copy files to and from a standard USB memory stick that you insert into the top of the instrument. Let's start by saving the current instrument state into the internal memory so we can quickly recall it the next time we're out on site. So I'll press Shift and File, and if we press Save As, we can select Trace, or in this instance Instrument State, an STA file. I'll change the name, I'll call it A001, and press Enter. You'll see here that the file A001, which is a state file, has been saved to the internal memory. You'll see here the media type is internal, and it was saved at 1:45 in the afternoon on the 30th of April. Now, if we get out of that screen and I press the Instrument Preset button, simply by pressing Shift, File, we'll scroll down to A001, and I press the Recall button, and you'll see the instrument has immediately recalled all of the instrument settings that we'd previously been using. Everything from frequency span, amplitude, attenuation values, even the automatic measurement that we had for channel power. Not only does this save a lot of time when you're out on site, but it also increases the quality of the measurements that you and your team are making, because it means that the same measurement can be made the same way every time, regardless of the operator and regardless of which instrument you're using. So we're out on site and we've made the measurement that we want, and now we need to save the screen capture of the results for including in a report or emailing to a client. Now there's a very quick and easy way of doing this, but I'll just show you how to set it up first. If I press the Shift and File button again and press the Setup button, you can see here there's a setup for what's called the Quick Save. The Quick Save type of file is currently set to JPEG, and Quick Save auto naming is off. I'll turn it to on and then press Return, and we'll go back to the main screen. Now, to save that screen image as a JPEG file in internal memory and for copying later onto our USB memory stick, all I have to press is Shift and Save, and the instrument prompts us automatically with a name, and here you can see the file name ends with _5. I'll just press Enter. The instrument's now saving that JPEG file to the internal memory. And if we then decide to make another measurement, and I want to save the results of that, I'll just press Shift and Save, and it prompts us with a new name. The same prefix as before, but now _6, so that's the auto-naming feature in operation. And for those of us involved with defense and security operations, be aware that if you order option SEC, Secure Erase, you have the ability to perform a low-level format of the entire user memory and delete all user data. This is made possible by the careful design of the N9343 series of analyzers, where user data is stored completely separately from the internal system memory. So with option SEC activated, all user data can be permanently deleted and cannot be recovered. Ideal if you need to send the unit off-site for any reason. Up until now, we've been measuring devices that actually generate their own signal, such as a transmitter or a signal generator. But what happens if we want to measure a device that doesn't generate its own signal, such as a filter or an antenna? Well, I have a filter here, a duplexer or diplexer, which you commonly find at base stations for separating the receive and transmit signal before it goes up the antenna. In fact, it's two filters. So how do we go about measuring that? Well, if you have the tracking generator option installed on the analyzer, that generates a signal out of this port here, which sweeps synchronously with the receiver sweeping on the analyzer. So if we connect the signal out from the tracking generator into the filter, and from the filter back into the analyzer, we should be able to see a frequency response plot of this device. So I've connected the tracking generator output to one of the inputs on the filter, and the output from the filter to the input of the spectrum analyzer. Now, don't forget, if you're measuring a 3-port device such as this, remember to terminate any unused ports with a 50 ohm load. So to turn the tracking generator on, we press the mode button and press tracking generator. and we'll turn the tracking generator on. So let's set a center frequency of, say, 430 megahertz. And then I'll press the span button, and using the arrow keys, I'll just zoom in, and we can look at some of the detail here of the filter. We can see that it's a notch filter, and there's supposed to be a pass band here. One of the cavities of the filter looks like it's not lined up properly. And if I press the marker button and turn the knob, we can move marker 1 here down to the notch of the filter and see approximately what frequency that notch is. Now you'll see there's quite a bit of noise at the bottom of the notch there. So let's see what steps we can take to improve the sensitivity and hence the dynamic range of the measurement. Well, if I press the measure key, you'll see that the amplitude of the tracking generator is set to minus 20 dBm. So let's select that and increase it to its maximum value, which is 0 dBm. And now you can see we've gained about 20 dB of dynamic range. There's still a bit of noise at the bottom of the notch there though. So let me just zoom in. I'll press the span button. There, you can see it there. Now, like with spectrum analyzer measurements, we can also reduce the attenuation. You'll see here the attenuation is set to 20 dB. So if I press the amplitude button again and set the attenuation to 0 dB, you'll now see we've got a much improved noise floor and hence dynamic range, and we can clearly see the shape of the bottom of the notch filter. Now, those of you that have done network analyzer measurements before will know that we're never making an absolute measurement of a device, we're always making a relative measurement, comparing the frequency response of this filter with a known standard. In this case, I'm going to use a type N through bullet adapter. And this is a good opportunity to point out that for making network analyzer measurements, the quality of your measurement is going to depend very much on the quality of the adapters that you use. So rather than getting a cheap one from the local electronics store, spend a bit more money and go and get a good quality one that you keep with the instrument for this kind of measurement. So I'll disconnect the filter and I'll connect the through adapter. And if we press the measure key and then normalize, store ref 1 to 4, that saves the trace into the memory, and then press normalize on, the instrument has now normalized this trace. The trace is now at exactly 0 dB, right the way across the top of the screen, and is removing any losses or errors from the cables and adapters and the rest of the measurement setup. I can now disconnect my through and reconnect my filter. And now you can see the normalized insertion loss trace of the filter with a good clear indication of the shape of the notch. If I press the marker button, we can move marker 1 down to the bottom of the notch filter there. I can turn on a second marker and perhaps measure the insertion loss of the passband. And of course, most importantly, we have a very fast sweep time, 44 milliseconds, quite incredible for a handheld analyzer. So if the filter needs tuning, we can make adjustments to the filter by adjusting the various cavities and tuning it up. If you're involved with the rollout or installation and maintenance of a new radio network, you're likely to have to make the same measurement of the same device many, many times, whether it be a cable, antenna, transmitter, or diplexer filter. The limit line capability on this series of analyzers makes this task incredibly simple for minimal effort up front. Here I'm measuring the same duplexer or diplexer filter that we measured previously, but I've created some limit lines. You can see here I've created a limit line around the passband and the notch of this filter, and where the measurement of the device passes and meets the specification, the trace remains yellow, but where it doesn't pass, the trace goes red and we get a fail indication on the top of the screen. Now you may think this is complicated to set up, but in fact it's incredibly simple. To get there we simply pressed Shift and Limit, and we're looking at the limit 1. We can have 2 limit lines in place, set either both as lower limits or upper and lower, which would be the most common. And if I go and edit this limit line here, you can see it's a simple table here. I've entered 5 points, 5 different frequencies and amplitude values for each of those points. You can see the dots here on the screen, and the one I'm currently editing is the white one. So for example, if I wanted to change the frequency of this limit line point here, I can simply use the arrow keys or type in a new value. Once we've done that, we can press return, and we can save that limit line file into the internal memory of the analyzer or onto a USB memory stick, and then recall it at any time in the future, and always make sure that we're therefore testing these filters, or it could be an antenna, cable, or even the modulation characteristics of a transmitter, to make sure we're testing them all the same way every time. Now you'll know if you've got one of these Agilent U2000 series USB power sensors that not only is it a power sensor, but in fact it's a complete power sensor and power meter all combined in the one unit. And in fact the connector on the end, rather than being a normal power sensor connector, is a USB plug. So you just plug the unit into your laptop PC and it converts it into a microwave power meter. In this case I'm using the U2002A, which covers 50 MHz to 24 GHz. But you can also plug them directly into Agilent's handheld spectrum analyzers. We just press the mode key and select power meter, and I'll plug the USB lead into the USB port on the analyzer. You'll see the power sensor has been recognized and is initializing. And it's a good time to point out that unlike a normal power sensor and meter whereby you have to manually enter the calibration factors for that particular sensor into the meter to get an accurate measurement, with the U2000 series the power factors are automatically loaded in, they're stored in memory inside the unit, plus you don't have to zero or calibrate the sensor, it's auto-zeroing, auto-calibrating. So the sensor is now recognized and it's all working. So let's connect some RF to the sensor input. Now you may ask the question, why would we want to use one of these microwave power sensors with a handheld spectrum analyzer? Well, there's a couple of good reasons. First of all, it extends the frequency range for amplitude measurements of the RF spectrum. Secondly, a power meter is always going to make a far more accurate measurement than any spectrum analyzer ever can. So with our handheld spectrum analyzer and the U2000 sensor, we can make RF level measurements with the ultimate accuracy. Now don't forget, before we start making an accurate measurement, we do need to tell the analyzer what frequency the signal is that we're measuring so that it can load the correct calibration constant. So I'll just press Measure Setup and select frequency, and I'll enter 21 GHz. And now we're making an accurate, calibrated power meter measurement of our 21 GHz signal. Now, as well as the graphical display here with the meter, you'll see as the level goes up and down, such as in the situation of microwave fading, we can see the level decreasing and increasing. It shows the measured value in dBm and also in watts, in this case 8 microwatts. It also shows the minimum value or minimum amplitude that the unit has seen since we started making the measurement, and also the maximum. Again, very useful if we're trying to characterize path loss or fading situations. But what's even better, if I press return and press Mesh Display, you'll see here that we can change the display mode to a chart recorder. On the chart recorder display, we have time on the x-axis and power in dBm on the y-axis. So if we're trying to track, again, a microwave fading situation, as the level drops down, you can see that we are recording that on the chart recorder display. And of course we can then save that historical record of the changes in microwave power level to the internal memory of the analyzer. For further information on the N9343C, just go to the website shown below. Here you can download datasheets, manuals, a copy of the demonstration guide, and even request a free copy of the user training and applications tutorial DVD I mentioned earlier.